And some of you, we had our survey. There were around 35% of you who have never collected SAXS data, or never been to a synchrotron before. And the downside of this whole mail-in program is you don't come, and we don't get to see you, we don't get to talk to you. And these synchrotron things are fantastic. They're really wonderful to visit. Take any chance you can. They're great to walk around, and there's just so much science going on. So really recommend it if you haven't done it. There's a few confusing. We're at Lawrence Berkeley Labs. I'm somewhere in this office over here. Unfortunately, a big redwood tree blocked my view, so I can't see anything except big green stuff. But a beautiful place to work. Really lucky. That's in Berkeley. That's light source. And then there's the advanced photon source in Chicago. So these get mixed up a little bit because of their naming. This one was built in a cornfield. This one was built on a mountain, which adds extra differences. Um, each of these major synchrotrons that you see in front of you have SAXS beamlines. And so if you're not receiving the time you need, you could explore these other resources. Advanced photon sources in Chicago, and SLS2 is on Long Island. We have another partner Beamline or a synchrotron in Stanford, and then under the football field in Cornell, there is the chess ring. All of them have their accessibility issues, sort of maps it out. We are one of the very few vaccine lines that runs a full mail-in service. All right. There are many places you can also collect SAXS data. So there are in-house sources, the synchrotrons, which we're at, and then there's free electron lasers. There's pluses and minuses about all these things. So there's some nice in-house sources. They're obviously easy to access, but it's just like any other instrument. You need a staff person to keep this going all the time. It may not have the latest and greatest detectors, etc. It's got a little lower flux. This may have gone up by now. And then, it's kind of prefabbed, so you're not going to have an engineer come in and help you with your own sample stuff, which you might at a synchrotron. This is a synchrotron here. I'll get into a little bit. Basically, what happens is the electrons spin around, and as the electrons make turns, they emit very bright light. The disadvantage, of course, is regulated access. But an advantage is that there's dedicated staff to help you out, like us, and you don't need to pay for those people. We have higher amounts of photons, and what hopefully you notice here is that there are lots of other techniques that go around, and that's again why we recommend if you have a chance to come out and visit, you see all these other multiple techniques. Um, for us with SAXS, the experiment generally takes, maybe 20 minutes for SEC SAXS and 5 seconds for high throughput SAXS. So coming is not necessarily for just doing your experiment is not needed. And so we've opened up mail-in. If you want to come, you can come. What we do recommend is 2-week stints, right? So if we have lots of great lab equipment besides our synchrotron. If you want to come by, especially for those of you in colder places in February, we got like this 2-week period in February that's really nice. Please come by and set up your experiments. Then there's the LCLS, which is a big linear X-ray source. If you fly over the Bay Area, you will probably see this while you're flying over. Starts out, I think it's 2 miles long. This unfortunately is very difficult to access. You're there, they will not allow you to do routine experiments there. And the staff is meant to support crazy different things, so you might not get somebody specialized in what you want. There's only one technique at a given moment, so it's like one beamline, but the flux is just fantastic, right? many, many orders of magnitude higher than anything else that you'll see anywhere else. So for those specialized experiments, you'll see these charts here. This is X-rays are somewhere, I don't know, what are they? So we're, yeah, somewhere in here, I guess, is 10 keV. Yes, yes. Yeah, right here somewhere is where we're collecting in X-rays. And these are all the different fluxes, and these are the home sources, the molybdenum, copper, K alpha, sources, SSRL, the Stanford one, ALS, where we were at. And then there's these upgraded sources. So the APS just upgraded to this region, super hard X-rays, super high fluxes, and you'll hear that the ALS is also going through an upgrade and is going to go over here. Again, this is sort of each color here represents the different types of science that's done at the advanced light source. Blue is biology, the rest is like condensed physics or energy science or chemistry or earth science. So just a whole bunch of different beamlines, different techniques, doing different things. At the advanced light source, there are beamlines that are dedicated specifically to biology, which I've described here, highlighted here. The one that you're using is SIBYLS, the SAXS beamline, and that sort of sits over here in the dark, like the almost fully blue path here, almost fully dedicated to biology. But there's some tomographies, crystallographies, footprinting, infrared that are done here as well. All right, a little bit about the synchrotron. So this is a view of it from the top. Again, spinning electrons. If you look into this section, this is where the electrons are going. The electrons have made a bend somewhere around here. That is pumping light down towards these hutches, these rooms, which are the beamlines themselves. This is what the segment between where the electrons are spinning, and there's tons of radiation, and there's a big radiation wall. So there's a port where it comes out, and between here and the hutch, it kind of looks like this. And there's all kinds of optics that are setting up the beam. This is our optics, where we're focusing the beam, and we can focus it in a couple different spots. But the wall of the hutch would occur somewhere around here into that. So then inside this room here, where the beamline are, it kind of looks like this. And I've got, a little dated picture here, but we used to be a joint SAXS and crystallography end station. And during the ALS upgrade, we're going to make it all SAXS. But yeah, this is roughly when SIBYLS was born. It kind of looked like this. It's a little messier now. And we are decommissioning the crystallography. That's moved over. All right, so let's start with some small angle X-ray scattering. Any questions about synchrotrons? Because I'm leaving that now. All right. If not, here's where I start talking about the small angle X-ray scattering. So depending on which technique, SEC or high throughput you're running, you need some small amount of volume at meg per mil concentrations. Again, they differ for each technique, but roughly, and let's just say you would need to put this in front of a beam. The advantage is that there's no freezing or crystallization or on a surface issue. So one of the main assets of small angle X-ray scattering is the super easy sample prep, right? So you could send us a liquid solution and we would get small angle X-ray scattering data from it. Now, it really is helpful that you do some purification in there and are looking at one homogeneous molecule, because the SAXS signal is going to be from everything that's in this tube. Absolutely everything that's in this tube is going to contribute to your signal. So we got this synchrotron generating X-rays. It's hitting a liquid sample. it is most of the beam just goes straight through and does nothing, but a small fragment of it scatters. And that's the small angle X-ray scattering. And that's why there's a large distance between the sample and the detector where we're detecting, because we want all of the scattered rays to spread out as much as possible over a longer distance, so that we can get the data and separate it from this 10 to the 13th beam. You might have a single photon out here. So you really want to separate that. You don't want any noise or jitter from the beam to contribute to that signal. The signal is symmetric. In other words, these guys are spinning in every single direction relative to the beam. So there's no handedness or order in this. This is all going to be circularly symmetric data. We could just take a single line from the center of where the beam is hitting to the edge of the detector and get our small angle X-ray scattering. That would be this line here. So this would be X-ray intensity as a function of angle. But to improve our signal to noise, and again, like I said, there's one photon heading out here, but if we collect all of these photons around a ring, that means more photons, so our signal to noise is very much improved. This line, this scattering line, is directly related to the conformation of the macromolecules or the structures of the macromolecules that are in the tube. And so what I'm showing here is a protein MR11 going through some conformational changes involved, usually triggered by ATP and DNA interactions. But each of these morphs between the two states leads to a different small angle X-ray scattering signal. The downside is that this is a non-intuitive signal. You can't go from this little curve and give us this molecule. It would be very challenging, even for the experts in the room. This particular changes, we can say, okay, it's going from something elongated to something more compact. I think some of us with an eye and years of experience can do that, but it takes a bit. So this is a classic inverse problem, and that's defined by raw data that's not interpretable as an image directly. Instead, significant processing using mathematical models required to obtain an image. We're getting about 40 delivered parameters in this curve, but to define every atomic position in here is thousands, if not tens to hundreds of thousands. So this, you can't go from this SAXS curve directly to this ab initio. But, and as we'll hear from Mikhail later, this is the kind of perfect thing for AI, for like alpha, and if you have like an AlphaFold model to start with, you can kind of refine and stuff. So this is the kind of thing that we're playing with. But the important point from this slide is a direct relationship between conformation and the SAXS profile. A little bit about how this is, the little trick about it is that you can't just take, in order to get the most out of it, you want to subtract a buffer away from it. So this is a buffer, this is the SAXS sample with protein solution in it, and these are the SAXS images. So buffer would be the black line, something with protein in it is the red line. When you subtract the two, you get this green curve. This allows us to really focus in on the signal from the protein. And the X-ray beam's 10 to the 13th photons, right? So it has sometimes a little fuzziness to it, so it kind of bleeds out. And if you don't subtract that from the sample, it just over dominates it, right? So this is where the subtraction comes in. Typically, this is displayed, and I'm going from a linear scale here to a log scale here. And what I want you to notice here is that at the higher angles, at these angles out here, the difference between the buffer and the sample are tiny. The differences out here are large between buffer and sample. So, you really need super duper sensitivity. I'll get into why there's a Q-axis here. So it's X-ray intensity as a function predominantly of angle. So this is your angle as you go out. There's a wavelength component. So regardless of what wavelength you're collecting, it should look the same. So if we're collecting at 10 kV or 6 kV, I'm sorry, I should say angstrom. So if you're collecting at 1 angstrom data or half angstrom data or 2 angstrom data, these curves will all look the same because it's divided here by this. And this looks like Bragg's law. So this is kind of where that's coming from. Let's see. What other point did I want to make here? Yeah, I think that's the basics of the experiment. Any questions about the basics of the experiment or the setup? All right, so there's a little water spider here. You can imagine the SAXS experiment a little bit like this. There would be a plane wave coming in. Somebody's moving the water up and down. It hits the 4 legs of this water strider, and it produces these interference Fresnel things. And even if this were spinning around, you would still get some oscillations. It sounds crazy that it's not completely just uniform spherical if this guy were spinning in the water when the plane wave was coming in, but it's not. There's more intensity coming forward, and then there's some oscillations due to the correlation between the 4 legs at any given moment. And so that sets up our SAXS signal. Now, if we have that plane wave coming in, that plane wave is said to have some kind of momentum. The moment that some of those energy from those plane X-rays gets tossed to an angle, momentum has been transferred. So this Q that you see on the x-axis of scattering data, it's measuring the momentum change of the photon. And again, this is not really all that important. For the whole time, you can think of it just as scattering angle. But I'm just telling it to you so that you understand when people talk about momentum transfer, that's what they're talking about. So for all practical purposes, just say it's the scattering angle. And that's fine for most of it. So if you take this series of water molecules and you decompose the scattering signal from this, if you just had an atom, it would have a scattering signal, and this would truly be uniform, and that is plotted here in red, let's say. And then there's these tiny hydrogens popping out, so there's a correlation between the hydrogen and the oxygen, not much because hydrogens don't have a lot of electrons, and they're mostly centered. So that affects the scattering a little bit, and it would be a little different. And so these are, so the first term just per atom is this term, and then organization within the macromolecule is this term. And then for water, the water molecules are correlated with one another, and that sets up another term here of molecular interactions. And that would give you this black curve here for small angle X-ray scattering. And those of you who collect crystallographic data will recognize this peak. This is your water ring that you see in your crystallographic data as a function, again, of angle. The thing that we're interested in is just what the single molecule looks like, right? What does the protein look like? What is we're not interested in necessarily in how the proteins interact with one another over distance. Some of you do, but very few of you do actually, about this sort of interaction over distances. At high concentration, maybe these proteins are bumping into each other, avoiding each other. Usually this term here is not of interest, and we're really focused in on the intramolecular organization of a biomolecule. Yeah, and so I guess what so as I showed in that slide where the protein is moving back and forth, it's all math. The intensity at the scattering angle is related to the electron density of the object that's doing the scattering and the position and the distances between the atoms. So this is all just math, and not math you can do in your head, but math connecting the two. And fortunately, you don't have to write that math. That math has been written for you in programs. So yeah, let's see. Yeah, I think so. This is lysozyme, and all these equations are true whether you're doing X-rays or neutrons. So this is a lysozyme being rotisseried in an X-ray beam, and this is the X-ray scattering that's going on here. And hopefully this is coming through. And this is courtesy of James Holton. And like I said before, this is just doing math, right? Plugging in the electron density and the orientation of the X-ray beam relative to the electron density. And you can see the beautiful pattern. And I think he's got colors for phases of when light's hitting. So this is the rotation here. When we do our small angle X-ray scattering, this molecule is accompanied by all the other ones around it in all other orientations. And not just, I'm just rotating it around a single axis, but all axes. So all of these nice sort of features all get averaged into rings. And again, that's your scattering angle. So again, for SAXS, all we go is from the center out, and we get the same pattern if we went from this center out, or this way or that way. It doesn't matter. It's the average of all of these things. This is, yeah. So when you have a single molecule, let's say you're collecting at the free electron laser at LCLS, where you're spurting in by atomization a single molecule. This was what it was built to do, like originally justified to do. And you have this nice vectorial relationship between the intensity. Here, I'll go for the intensity. So it's math again, just electron density here. All the atoms in one, it's this far away and in this direction. So that's this R here. And then the X-ray beam is coming in with this intensity and in this direction. So these are got this nice vectors. And this would be like the Ferrari of your measurement. Like if you could do this, you would have absolute access to your everything about your protein. Unfortunately, again, there's this rotation going on. And that means that we have to put this beautiful term, this Ferrari, into a circular averaging. This is what these triangular brackets mean. They are circularly averaged. If you take this nice vectorial term here with vectors, like it's at this position and in this direction, once you put these triangular brackets in there, you lose your vectorial nature. You become a scalar. Which is, again, what's really going on, right? So the thing to notice is that if you're going, let's say, and crystallography also, like you are able to hold those molecules in one position relative to the X-ray beam. So that's, again, a Ferrari type experiment. Because we're rotating in every direction, we're averaging things out. You lost your vectorial character, and you now end up with scalars in here. And so the intensity as a function of angle, or this momentum transfer, or this Q value that we call, is related to the structure in this way, no vectors involved. And this P of R function has all of these this information, this how your electron density is organized. Okay, for small angle X-ray scattering, this function, which has all of the electron density association of the molecule that's doing the scattering, this P of R function is really, quote unquote, exciting. Okay, it's an exciting function for us. If we were able to get that, that's about as good as it gets. And while it is math, there's a simple term for it called a Fourier transform, and we've got great tools to perform Fourier transforms. So your intensity is a Fourier transform of all the stuff that has the position of the atoms in it, this P of R function. And since the molecule is finite, it has a maximum dimension, this works out, this integral works out. So here are scattering profiles, and then doing a Fourier transform to extract this P of R function, you get these curves. And right away you can pull out the maximum dimension of these particles, and these are 4 different proteins, and you can see that they have very different P of Rs, and you will gain intuition about these P of R functions. So, that's the maximum extent. And just to give you some idea here, if a globular protein will have a nice Gaussian P of R function, or Gaussian-like, this is probably, if Antonio here, he's call it a Voigt function. Um, DNA, which is a long linear molecule, it'll have a peak because there's a lot of electron correlations along the central axis of the DNA. So that'll have a peak early, but then because it's long, the Dmax is really stretched out. So you can tell from this P of R function, it's a elongated particle. And for this bilobed protein, it's long, but it also has intradomain distances and interdomain distances, and those appear as 2 separate peaks in the P of R function. So it's telling you about the distribution of your material. I'm keeping track of time here. So if you have this molecule spinning in all orientations, this is a toy model, there's some degeneracy that occurs here. And so the distance between atom 1 and 3 is the same as distance 1 and 4. This happens to be the longest distance, but because it's the same, it all gets binned up into one, 2.5, or let's say 2.5 nanometer thing. Sorry. There is the distance between 3 and 4 is unique, and the reason it's doubled is just the way that math works. There's the distance between 3 and 4, and there's a difference between 4 and 3, right? So that gives kind of double significance. Each of them does. So that is represented by a small bar, and then again, you have 2 and 4 and 3 and 4. Those are similar, so those get binned up together. You can't distinguish which pair contributed to this column. You just know that there's a lot of pairs that are this distance apart, and then there's one unique distance between 1 and 2. Now, this is a powerful and exciting function, as I mentioned. If there's any change in the organization of this grouping, this toy model, you will see it all in this P of R function. So these curves, this guy moving down will change the P of R function, or if it moves further out, you get a different function, or if it comes closer in some way. These are all very distinguishable from one another. So it's very powerful for detecting conformational change. There's one annoying flaw to the P of R function, and you'll notice it right here. This is finite. Your P of R function is finite. It's got the maximum dimension. But in order to do a true Fourier transform, you want scattering data to infinity. Okay, that's how that math works. It goes out to infinity, and we do not have, wraparound detector that can collect all of the data. So there's this way of getting around that. And this is why you have to use, it's not all super automatic and trivial to get your P of R function. And you'll notice that when you get your scattering curve and you try to dump it in the P of R function, you have to tweak it a little bit. And I don't think I have enough time to really go through the details, but what it is essentially they're going to, in a nutshell, assume that the P of R function is a series of of Gaussian spline functions, and that if you stack these next to one another, there's a smooth, a little bit higher and a little bit higher and a little bit higher. So there's a smoothing function between these equally spaced Gaussians that are fitting the P of R function, and they also do a cubic spline to represent this Gaussian. And that's because when you chuck each of these terms into this integral, it's integratable. Shoving a true Gaussian in here is a nightmare to compute. So they do a cubic spline representation. So anyway, it's a little more complicated. And you have to always remember that your P of R function is a fit to the data. It is not the data. And you always have to examine the fit to the data to make sure it's fitting the data, and not just, that's what it is. And lots of mistakes have been made because people assume that that's what it is. And you'll see that all the tools that we have fit the scattering data, not the P of R function. Um, and that's because you're fitting the primary data when you're using the scattering data. Oh yeah. I kind of covered this a little bit, how much information is in the SAXS curve and what can you hope to really extract from a SAXS curve. Well, let's say you have perfect data. It turns out somebody's done this calculation for you. It's about 40 unique pieces of information, but you imagine that as you get noisier and noisier and noisier, you're losing information. So noisy data, less parameters. And from noisy data like this yellow curve, the best you can hope for is maybe the radius gyration and maybe that it's folded. But as you get higher signal noise, you get more and more information. And again, that's the value of coming to a synchrotron, right? Is that you hope to get this kind of quality data. So there's only 10 to 40 constraints. There's no way you can hope to extract your full atoms and positions. And so that's why it's really important for you to come in with some idea of what it is. Obviously, we're dealing with atoms. Sometimes we're dealing with DNA, sometimes we're dealing with proteins. If you say it's a protein, there's a lot of information we know about protein. It's got a certain bond length, it does helices, it does beta sheets. Those are all additional information that all of our tools are using to, with the SAXS data, in partnership with the SAXS data, to constrain the solution, right? And so if you know you're fitting a car, you want these dimensions. If you're fitting glasses, you want these dimensions. So you look to the SAXS data as constraints on what the object is. The days of which you would use SAXS for ab initio reconstruction, like absolutely, I have no idea what this is, are it's just not possible to do. And again, this is why this partnership between AlphaFold or structure prediction and SAXS is so powerful, is because you can come in kind of an idea of what this is that's doing the scattering and ask about whether those dimensions from the prediction match the things from the SAXS data. And Mikkel will tell you about how to extract all of these parameters using a tool in a moment. I wanted to mention that, and I've mentioned over and over again, that the math is done for you. So there's this tool that Mikkel and the Sali Lab worked out. It's a web form. You go in, you choose your PDB. It could be AlphaFold prediction or whatever. And you can also put in what you've measured, the SAXS curve, and hit submit form, and it will calculate the SAXS that you would expect using this math and plot it against what you measured. There are some details here. The water around your protein is more ordered than the water in bulk. So there's some fudge factoring about that. Maybe it's a little more ordered or a little less. So there's a little bit of that going on. And that's where adding your experimental profile will allow you to tweak those options. But yeah, you can check these out. There's some, let's say you have 20 models that you're feeding in. You've got one SAXS profile and a bunch of predictions. And you want to know which one's better, and you put that all in a single PDB. You can choose these options to separate it out, etc. And you can download that scattering profile. So again, very sensitive. So this is a protein with 2 domains and a loop that comes out. And so this is the open protein, open cap structure. And then way down here, the 2 domains have come together and the loop is closed, and all the permutations in between. And all of these give different SAXS profiles. So again, this is where the power of SAXS comes in. And that buffer subtraction is really key, right? So you need that if if in these high Qs where the signal is very small, difference between your buffer and your sample are very small, if that buffer isn't properly matched, you might wipe out these little differences that have these details in them. So that buffer matching is a really important part for your interpretation later on. And so the classic thing you do, you have your atomic model, you make your SAXS comparison, there's a dash curve here, it doesn't fit, you modify your model, create the dark, solid black curve that fits much better, and you've done, you've improved what you had. And you'll learn all about this, you'll collect your SAXS, you'll have some computational structure prediction, you'll run into Fox, and you'll compare them. And then Scott and others and Mikkel will go over BilboMD, which allows you to ways of tweaking the structure to get something that fits nicely. All right, I think this is my last slide, Mikkel, so don't get too worried. I had a very prominent scientist ask me this question: what would I do with SAXS that I can't do with cryo-EM? And of course, that's on our minds a lot. If you just want one structure from scratch, and you're just interested in this novel gene, you might as well spend the 3 years, 2 years to do the cryo-EM and get every single atom position or crystallography, of course, in that structure. Okay, that's it. But if you're interested in that structure as a function of different conditions, for example, and you want to see, and you have the structure already, this is a very powerful tool. Also, you can do all kinds of additions of your metabolites, ATP analogs. Let's say it's an ATPase. You want ATP, ADP, AMP, non-hydrolyzable analogs. You can all do that very quickly with SAXS. You might want to use small angle X-ray scattering to guide you to something that's crystallizable or cryo-EMable, right? So you might be starting to truncate the protein in different ways, and you might have a whole panel and you're looking for the condition. Maybe it's a particular salt concentration that allows your DNA protein complex to form. You could do a screen here to identify what would be best for cryo-EM. Cryo-EM does have biases. So let's say, particularly for lipid nanoparticles or, some proteins lay on the grid in a different way, or because of the freezing process, it's in a specific conformation. You might be biased. And the SAXS data, because you might get your cryo-EM structure, you could throw that against your SAXS data and see whether you've been biased. There might be concentration-dependent effects. So on a cryo-EM grid, you want lowish concentration, but sometimes affinity for complex formation may require you higher concentrations, and SAXS would be good for that. There's all kinds of time-resolved experiments, transient states, and there's all kinds of specific circumstances like pressure and like activation, small proteins, of course, and proteins with flexible regions. And that is it. Let me escape from here and hand it over to Mikkel. Before I do, are there any questions? If not, Mikkel, I have exceeded my time. I apologize. Let me stop sharing. Can somebody throw up a thumbs up just to make sure that you guys are there still?
Yeah, we are here.
Well, thank you guys.
Okay. Well, I have a 10 minutes, so that's gonna be fast, but
you can continue, Mikkel. Give your talk.
okay. No, I just rather not really talking about the slides. I think this is, so I introduce myself, Mikkel Hamel. I'm a Beamline scientist at the SIBYLS, as Greg, a staff scientist at the Lawrence Berkeley National Lab. And I thought this is not a 4-day workshop, what we normally supposed to do. This is just really give you idea what you're getting from SIBYLS and how to read the informations or the packages that you're getting through the simple scattering database. So before I'm going to some kind of slides, because great introduction, so I will tell you exactly how to read or how to communicate with us, and what do you get from us that you can continue to analyze, and how to analyze it. So first of all, what kind of package you get. So you probably, those people that didn't collect or would collect already, they're getting emails from us from the simple scattering database. So here is probably one deposition called whatever XY blah blah blah. There is the lab name. Sorry, I'm using some of your information here, but this is all non-proprietary stuff, so we can just show you and we get access to it. And you get the zip files, two zip files. One is the name of the sample and called result zip. When you downloaded this package and you open it, hopefully I'm sharing the screen. I do. So here you have some kind of zip file. You can open the zip file. I make it a little bigger. Those are frames on SEC, something similar you're getting also from high throughput when you have numbers of dot files. This is the first exposure, 2-second exposure, then you go all along for 25 minutes. And every 2 seconds we expose your sample as is eluting. In this case, this is SEC SAXS data. Much more important for you because we've done most of the work for you already. And that's the second zip file called process data. And when you're uploading the zip file and you're opening, you will see a lots of PDF files, the dot files, the output file that I want to give you some introduction to this. So here is an example of the sample called KG12. And well, I will look first is your information from the moles. And that is here AFE8, that's a moles from VIE. That's a data package and raw data, but you also have a report here. That's the PDF file. Normally it's the name of the sample and some date. And so you can open that PDF file, and first what you see is your elution. So you see kind of elution profile. It's the light scattering is the red, UV is the green one, and then we also have a reflectivity index, what is the blue one. And so what you can kind of already imagine, there is some aggregations in the void. Our void is in between 8 to 10 minutes, depending on a column that we're using. And then you have a later peak elution of your, most likely the protein of interest, and another shoulder here. And so now you can go to the bottom if you want to skip all these informations here, but then you can go straight to this graph and the final report that's here. Then you have some hydrodynamic radius information about the peak 1, that is this one, and the little peak 2, that is done by Amici. And you're going to look at this molecular weight here, molar mass or molar mass moments or molecular weight. And you kind of already see it's 130 kilodalton, the first peak, and you see 70 kilodalton, the second peak. Now, most likely that could be a monomer dimer separation, but just guessing. You know more about your sample than we do. But this is the first what I will do, and you should do too, the quality of sample, the elution, etc., etc. The second part is this PDF reports. Obviously, you see a multiple. That's all your samples in the shift that you sent us, but this is a sample called KG12. So you go on a KG12 row report. That's the information that we analyze the SAXS data for you already. And when you click on it, you will have, you will have some information about, again, it's the same elution profile, but instead of light scattering, you have the small angle X-ray scattering. I'm gonna zoom in a little bit. You will see it's very similar profile where we confirm in a void that's about 250 frame. That's aggregation most likely, and then you have a nice separation of the second peak, and this little shoulder is this probably the monomer. And what we also do for you, we also merging few frames to improve the signal to noise ratio in the final merge data that you see in panel B. And that is shown here with this pink region that not only one 2-second frame, but multiple 2-second frames can be merged. And that is also because across the elution profile, you have the same radial duration for that peak for those few frames that we're merging together. And obviously, then we also calculate some Guinea region, that is the radius of gyration. And also very important is this panel D. That's the normalized Kratky plot, and that's I will talk a little bit later. And Greg was also talking about this p-row function that you also see the maximal dimension or overall shape of your molecule. So when you really don't want to go into details and you don't understand these curves, you may go to the tutorial of the raw. I will show that in a few minutes, how to grab this information and replot it for you. So what I will considering the summary table that's on page 2 of your raw report / name of the sample. In this case, just the main peak was analyzed. That's the first peak. And again, you compared these molecular weights here. That's the most important. Compare the molecular weights with your molecular weights from the moles. And if they are in a let's say 5% deviation, that's exactly what we want to see. Then you can see that molecular weight is exactly 40 kilodalton. I getting this question for during my office hours, which molecular weight should I report, I look at. We prefer, I don't want to go in details now, it's the VC, that's the volume of correlation calculation, or Bayesian. And in this case, you see that how perfectly they match, 38, 138, something. You also have information about maximal dimension and radius of gyration. You can compare radius of gyration or calculate from the Guinea, and we have also a way to calculate the radius of gyration from the p-row function, and you can compare those. They may be a little bit different, but I prefer just if you stick with the Guinea plot, that's mean reporting the radius of gyration. So that is already the first look at your package, molecular weight from the moles and molecular weight from the SAXS, and some kind of overall quality data you see here from these plots showing in your report. So you are already knowing a lot when you open your package. Well, obviously you're collecting multiple samples. SAXS is, as Greg mentioned, is all about comparison rather than I want to define the structure. Obviously with one curve, you can validate the alpha fold model that we're showing later. But most important is to compare your different experiments, your truncations, and let's just go to that point. And in this case, you upload audio deposited data that you're getting from us, and what you do, you open not the PDF, but you open raw. Raw can be uploaded, it's for free, and we have all this instruction in your README file before in your packages. So here I just plot a couple of data today morning, and I'm sorry I'm not prepared with the nice slides as Greg, but I think it's much more important. How you gonna do it? Let's say I wanna just plot the dot file. Okay, so instead of the PDF files, those are the reports. I wanna just look at my dot file, that's the experimental merge data, and I can put it here, grab it, and see it. So let's just show that only one. Don't remove, just hide. Hide. Okay, so here is my data. Final merge data sets. And you here in the right corner, you already see the values that are in the report, the molecular weight, the radius of gyration, with some standard deviation and maximal dimension. Now, let's say we want to compare this KG12 with the KG11. Here we go. That's already there. You kind of already see the lower intensity, maybe a little lower concentrations, but then you see also what are the values of in RG, maximal dimension, and they can compare those when you click in between, what the differences are. And based on the RG value, kind of estimate that these samples are almost identical. These molecules, the KG 12 and 11s are almost identical in maximal dimension and radius of gyration. Well, if you want to redo something, but before we're going to go to the redo something, Greg was talking a lot about the p-row function. That's the most important information. You can also upload this called out file. This is the PRA function. And again, you have all that in your README files. So sometimes I'm really puzzled why people don't read those, but people kind of users sometimes don't have a time. Anyway, so here is my PRA function for the KG12. And again, maximal dimension is where the PRA function goes to 0. Here on the bottom, you see the fit, quality fit of the Fourier transformations to your raw data. And what I can see here already, some kind of distribution of the electrons in your most likely protein. I believe this seems like a protein. So what I have, maximal dimension, residual duration, molecular weight, calculated for you, all is ready. Let's try to compare KG12 with KG11. As I mentioned in residual duration, they've been very similar. These are the two PRA functions. You can barely see it. I'm going to zoom in. They are for the samples. And yes, indeed, they are identical. Slightly differences could be due to more noise in KG11. But confirmed, yes. And there is another sample that I just want to show you, and I can go back to the here. You click on a profile, and you want to look at the, let's say, KG16. Whoops, and this curve looks completely different. And you can see it in the profile, but you can also see it in the residual durations. And that's exactly you can see in molecular weight. This is molecular weight is 12 kilodalton versus 140 kilodalton. So that's also where the SAXS is powerful. You're comparing data, comparing different informations. Okay, so that's the package. But let's compare the, sorry, we'll continue with the PRA function. So now we can compare the overall PRA function rather than just the values in residual duration. So now you can click here. And I think that was number 16. Is that correct? Yes. So this is already seen that the molecule is not only smaller from the molecular weight, but also from maximal dimension. And then also this is normalized on I0. So it's just showing the area under the curve is normalized on I0. Well, what information you see here is not only that is a different maximal dimension of your protein, but also that it's not extended, etc., etc. Again, we don't have so much time to really go in the details here, but so that's the package. That's what I would like to see that from you. You look at the molecular weight, you look at the PRA function differences, and you can kind of estimate if you can read some more details. I would show anyway one slide how, okay, before I go there, sorry, my apology. Mostly you want to also sometimes see what like how much unfolding, how much flexibility you have in your protein, because you do solution scattering because everything other failed if you do structure determination. And that's the Kratky plot that Greg didn't mention or mentioned a little bit. And how we can do it in your data sets is super simple. You already have a Kratky plots in your report. That's this Kratky plot on the bottom. Panel D, that's your Kratky plot. And you can also see that your molecule, in this case, is well folded, because if you read here at the bottom, the dashed line show where the global system would peak. And in this case, it's peak right across the dashed line. But let's imagine that you have a molecules, a slightly open, unfolding, or may increase the flexibility, and you can monitor that using this normalized Kratky plot. And I'll give you some example here. And here we go. Here are normalized Kratky plots for different macromolecules, and also subtle changes like this silanase versus glucosamines tell you that silanase have a little bit more flexibility because the peak is shifted, but also the tail of the Kratky plot is a little bit more extended. On the other side, we have something what is much more flexible. Those are these RNAs that you see that it's not very hard sphere. That's the green and the pink one. The same riboswitch can bind ligand called SAM. Let's call it same riboswitch. And you already can compare the ligand and non-ligand bind state, where the ligand bound state is much more different, is rigid, because the tail is going down versus the without ligand, the tail of the Kratky plot is going up. There are some extreme cases like this RAD51 AP that seems to be not folded at all. And it's also very similar Kratky plot to the SEM riboswitch without magnesium. SEM riboswitch is RNA, so you need the magnesium to be folded. So all that is all about the comparison. Sometimes this is only information what you need to know, and you don't want to do any structures, especially when you do some unfolding intrinsic disordered proteins, like for example RAD51, you will not do structures of unfolded proteins, and you're just comparing a flexibility level with and without the ligand. So that can be done also for your sample KG. Let's just select one of those as a primary, and then we can select those data and say, here is a button, right click, help all the time in a row processing, and that's the dimensionless Kratky plot. When you click on this, obviously very large angles there, that's why producing this white peak, but you have this zoom in, and that's exactly the region where you're supposed to focus. And we can also see now what's happening in the flexibility of these different molecules. I'm going to unclick a couple of those. It's much more readable. Okay, so the KG16 seems to be a much more, I would say there are some partial flexibility or unfolding based on the tail of the Kratky plot that is going up, versus the KG12 and 11. They seems exactly identical and a perfectly folded molecule. So those tiny differences are significant, and this is the best way to visualize the level of flexibility or unfolding. So that was the Kratky plot, and I will take one more minute. What can be done more with your package, and I will see if there are some questions. Again, if there are any questions I can bring up more data to really try to give you some information. What else can be done with Kratky plot, PRA functions, and linear regions? But more important is compare the data when you collect multiple data sets. Let's see if there is somebody in a chat. Now I can see anything because I'm in presenting mode.
Yeah, there was a question about transient interactions in SEC, but we might get to that later, yeah?
Yeah, we can. That was what I was thinking doing after the HD, talking about like how to compare transient interaction, how to see it in SEC and moles. Yeah, so that's most likely everything. Let's bring some more examples to this report at what kind of cases you may deal with. Let's just look at the sample. This one is identical. This one seems identical. Okay, so here is example of another sample called JKL-S5. It's from the last data collection before our shutdown. And there is also, I wonder if this is aggregation, as I mentioned to you, that during the SEC, we have void around 280, 250. So we're considering this already as aggregation, and you can see from other durations that that sample. So you need to decline my phone calls, perfect. So, but there is some potential to have some smaller, not aggregated sample. Unfortunately, these aggregations are so significant. So this scattering profile is need to be considered as aggregations, or separation on a column that wasn't a good choice. That means the molecule is bigger than 500 kilodalton because it was a column with a void in 600 kilodalton. And indeed, you still get some informations, but it's very questionable based on the molecular weight, even if it wasn't calculated, and maximal dimensions are super large. So this need to be done before you go to some modeling. Don't try to model the data like I show you in this case. That wasn't this case, but the sample JKLS5, something very large and mostly aggregated. Okay, let me open some other cases here that I was trying to prepare. Let's just go to the EB19. And again, those are the packages that you're getting. Hey, what should I do with this, for example? That's a sample called EB19. And yeah, there are some signal in the moles, but as you can see, multiple UV signals in a very low intensities. And I believe that was not really able to get any information out of this sample except that the void is there significantly higher than anything else what we're expecting in this region. So I will not even considering to analyze this data. That moved on, but just for comparison, how the EBG19 looks like on a SEC SAXS. So yeah, there is no signal detectable in the SAXS neither. So yeah, that was a failure. Maybe the sample was aggregated and we spinning our samples before we putting on SEC SAXS. Okay, let me find some other example that, and then I will end up with these examples. JKLS4, did I talk about it? Maybe not. Oh, that seems already written, aggregated here. Okay, so all those JKL seems to be not really useful, and all what you see just aggregations here. So I will not analyze those data. Maybe this one. Yeah, that was this big peak. Okay, well, after Greg gonna talk about HD, I will bring some more example how to really get the SEC data to analyze again if you want to redo your merging and you're more interested in much more advanced, maybe potentially deconvolution of peaks that are overlapping. That is also done for you as well in a fast way. But that's just the idea how you can open the data package in the raw and look at the basic SAXS and the MOS parameters that are done for you.
Mikhail, did you shove the link to raw in the chat?
I will do it right now if somebody need to upload it.
Yeah. And don't be afraid of raw. Raw, I mean, it's a godsend to us. It's a pretty simple tool to use. Much simpler than lots of things that you're going to encounter as a scientist. So,
I would like to also point in the raw have an excellent tutorial. If you, even the tutorial that have information about how to calculate the raw functions that is done for you, but you can redo it. Or how to look at the molecular weight, how to do radius duration, etc. So that tutorial is step by step, sometimes even too many details written in tutorial, but please upload the tutorial if you get the package from us. Putting it right now in the chat.
and the other thing for all you hackers out there, all of it is written in Python. We got to give Jesse and Steve credit. So, if you want to pull down a routine that pulls out your RG, that is an extractable piece of code. All kinds of that stuff is hackable and extractable. So, That's what's amazing about it. There's a question there, Mikhail, for you.
Okay, so you consider anything over attribute. That's not true. Depending, yeah. So the sample that I showed, that was really, it could be something what is large and not aggregated. Especially there is some signal that seems there is just really extended or enlarged. But for this sample that I show, it's seems to be in a void. A better choice to try to experiment again with choosing a different column that have the larger void. We have choice of our 3 columns. They are online in the mailing page in instruction, and allowed us you can choose. We have a Shodex K804 that go to the 1.5 megadalton, but we also have a very large void columns that go into the 6 megadalton. That can be also up on the request. It's not online. You can do some tricks with those columns as well if you're interested into something very large.
Yeah, if you're interested in something large, we've been after it, right? We got a couple tools. For those of you who don't know, we do a bit of lipid nanoparticle work, and those are very large things. We also do some virus stuff, also very large things. And so we've imported a bunch of tools. They're still quote unquote experimental, but we're always interested in samples. And so we also have a field flow fractionation system that we purchased and are testing. And that is supposed to be great for very, very large as well. So let us know if you got those big chunky things.